In this presentation, we are going to discuss representation learning and generative learning using autoencoders and GANs. An autoencoder is an artificial neural network that is able to learn dense representations, also referred to as codings or latent representations, of its input data in an unsupervised manner, and then converts the codings into a reconstruction of the input. An autoencoder is usually made up of two parts. The first part is the encoder network, or the recognition network. It takes in the input data and then converts it to its codings or its latent representations, which are usually of lower dimensionality than the input data. The second part is the decoder, also referred to as a generative or reconstructive network. It takes in the codings as input and then generates data that is very similar to the input data. An autoencoder has the same architecture as a regular multi-layer perceptron or a neural network. The number of output neurons, however, of the decoder should be equal to the number of input to the encoder because we are trying to reconstruct data that is similar to the input. The output of the decoder is often referred to as reconstructions, and the loss function of the network is referred to as the reconstruction loss. That is because we want to penalize the model when its reconstructions are quite different from the input data. However, it is worth noting that our end goal isn't just copying the input to the output or duplicating the input signal. However, we want the autoencoder to output data that is approximately similar to the input, and that is why we restrict the hyperparameters of the autoencoder, such as the size of the decodings or of the codings, in order to reach such an output. Common applications of autoencoders are dimensionality reduction, information retrieval, image processing, and anomaly detection. Next, we are going to discuss an alternative, more superior approach to generative models, which is GANs, or Generative Adversarial Networks. GANs are quite recent. They were first proposed in 2014 in a paper by Ian Goodfellow. When it was first published, it took the world by storm, though it took a few years for people to figure out how to overcome the difficulties that come with training GANs. The intuition behind GANs is quite simple. The main idea is to have two neural networks compete against each other in a zero-sum game, thus the adversarial label, in hopes that they would push each other to excel. GANs are generative in the sense that they learn to produce synthetic data that has the same distribution of the training data. That is to say that it produces fake data that is indistinguishable from the real data. GANs are used for several applications, such as super resolution, which is increasing the resolution of a certain image, colorization, or colorizing grayscale images into color images, predicting next frames in a video, and also turning sketches into photorealistic images. One very popular application of GANs is image generation, and a very famous example of this is the website This Person Does Not Exist. This website was developed by a software engineer from Uber as a personal project, and it builds on style GAN 2 from NVIDIA. The basic idea of the website is that every time you reload the page, a new image of a person pops up, and this person basically is non-existent. However, the images look very realistic, which just goes to show how accurate and powerful GANs can be. Now, let's actually look at different components of a GAN. A GAN is made up of two parts, the generator and the discriminator. The generator takes a random distribution of input, or typically Gaussian distribution, and outputs some data, usually images. The main functionality of the GAN is very similar to that of the decoder in the autoencoder in the sense that it generates data. The main aim of the generator is to trick the discriminator or to increase its error rate so that it produces images that are hard to distinguish from actual real images. Now, if we look at the discriminator, it actually takes as input either fake images from the dataset produced by the generator or real images from the real dataset. And its main goal is to try and tell them apart accurately. So here we can see that the main goals of both networks are conflicting, and that is why we describe this as a zero-sum game. The discriminator here offers the same functionality as a regular binary classifier where we have two classes, either fake or real. When dealing with neural networks, specifically when training them, we usually have a certain loss function that we want to minimize. So if our loss function is like this, our goal is to go down the gradient so that we actually reach hopefully a global minimum. In our case, we have two networks, but we are still gonna use one loss function. However, the generator wants to actually maximize this loss function, whereas the discriminator wants to minimize it. Thus, we have two phases of training. In the first phase, we are only training the discriminator, and in the second phase, we only train the generator. So in the first phase, what we do is that we feed some Gaussian noise to the generator, which then produces some fake samples, let's say an X number of fake samples. We then get an X number of real samples from the training dataset, and we mix those two together. We label the fake samples with a 0, that is to say that it's false or it's fake, and we label the real samples as 1. After mixing those together, we use the resultant dataset to train the discriminator using backpropagation, and we update its weights in a way that it could tell these two apart. The loss function we use is actually a binary cross entropy, since we are doing binary classification in this case. After finishing one epoch of this training, that is to say we passed over all of the training dataset once, we move on to the second phase of training, in which we only train the generator. So what we do again is that we feed some noise to the generator and it generates fake samples. Here we do not add any real images because we only care about the generator and its ability to trick the discriminator, and not actually about the ability of the discriminator to tell fake images from real images. So here we do not need real images. We set the labels of the fake samples as true or 1 because we want to monitor whether the discriminator was fooled into thinking the image is real or not. So our goal is to actually get a label of 1. So that's why we set the ground truth label to 1. We also use backpropagation to update the weights of the generator in a way that helps it produce images that the discriminator wrongfully classifies as real. It is also worth noting here that we are only doing the forward pass for the discriminator. We are not actually updating its weights, since if we update its weights in this stage, we would be purposefully training it to consider fake-looking images as real images, and that would be cheating. So we can see that in the entire training process, the generator never took a look at the training set. It never took a look at real images. So it didn't just take real images and learn to produce similar images. Instead, it learned this in a second-hand manner from the discriminator. It learned the information and the features of the real images through the gradient that flows back from the discriminator into the generator, and thus it learned to produce similar data. So actually here, the better the discriminator gets at distinguishing fake data from real data, the more it would learn about what makes the real data real, and thus this information would actually flow back to the generator, which can then produce real-looking images. Lastly, let's take a look at how we can actually train GAN in Python. So we can't just simply call a .fit function to train our model, since we have two different phases of training and we have two different networks to deal with. Thus, we have to create our own training function. In this example, we are going to use the fashion MNIST dataset as our training set. So our GAN is going to produce images that are similar to those in the fashion MNIST dataset. So we pass to our function the GAN, which is a compiled network made up of the generator and the discriminator. We give it the dataset, the batch size, which is the number of images that we train on in each step, the coding size, which is the size of our noise vector, and the number of epochs, which is the number of times that we are going to train on the entire dataset. So what we do is that we split our GAN into the discriminator and the generator. Then, for each batch in the dataset and for each epoch in our entire number of epochs, we do the following. First, we create an array of noise. We pass this array to the generator, which generates some images. We lump together the generated images with the real images from our batch, and we create an array of labels, zeros and ones, zeros for the generated images and ones for our real images from the batch. Then we set our trainable parameter of the discriminator to true. This means that here we want to train the discriminator, and we actually call our training function. We give it the images and the labels. So here we train the discriminator. Then we move on to phase 2. In phase 2, we also create some noise, normal noise, Gaussian distribution of noise, and we create our labels, which are all ones. Then we set the trainable parameter of the discriminator to false, since as you remember, we don't want to train the discriminator in phase 2. Then we call the train on batch function for our entire GAN, which will pass the noise to the generator, and then the generator will generate some images, pass them to the discriminator, and then look at what output we get, and thus the parameters and the weights of the generator will be updated. So here we can see the output images we get after just one epoch of training the GAN. We get images that are very similar to those in the Fashion MNIST dataset.